Okay, I want to now talk about an interesting pitfall that can happen with digitized representations of audio. Because we have to choose a sample rate. We have to say, I'm going to take 44,100 measurements per second of my audio, or 8,000 measurements per second of my audio. I can't take infinitely many. So if the pressure wave is varying too quickly, I may actually miss some stuff. It might kind of happen in between my measurements. So this leads to something that's called aliasing. Now, to build up to the mathematics behind this, I want to review some stuff that we did on Friday. So remember how I explained when we sample a signal and we look at the entire complex Fourier basis. It actually goes from a frequency index of 0 up to a frequency index of the number of samples minus 1. When we were doing the real DFT, we only went up to half, a frequency index of half the number of samples. But now we actually go up kind of all the way. What we noticed is, so here's an example with 40. We look at the cosine, so the real component on the left, the sine or the imaginary component on the right. What I notice is this mirroring in frequencies. So once I get halfway through, I start to get the same frequencies coming back the other way. But what we noticed was, okay, they are actually exactly the same on the cosine. So I can see this one is exactly the same as this one. This one is exactly the same as this one, and so on and so forth. But on the sine, yes, they're the same frequency in the mirror relationship here, but they're actually the negatives of each other on the bottom half. So what we can say is the coefficients of a real signal that we take a complex DFT of are the complex conjugate of each other. So let me actually write that down. We say that because the real part is the same, so in particular, the real part is the same for frequency k and frequency n minus k. But the imaginary part is the exact negation of between frequency k and frequency n minus k. So what this means is that the coefficients of the complex DFT, x of k and x of n minus k, are complex conjugates of each other. And this just means that the imaginary component gets flipped. Okay. So we can kind of see that in these plots here. I think it's also helpful to look at phasors and to understand a geometric analogy. So this is one of the things I went over in class as well, but it's helpful to see it again. So if I go and look at maybe an interval with 50 samples, and I look at a frequency that's supposed to go through 2 cycles over that interval, I can also look at the frequency that's supposed to go through 48, so n minus k. The one that's supposed to go through 2 cycles moves pretty slowly from one sample to the next. 48 cycles over 50 samples, that's really, really fast. I mean, you're going through almost an entire cycle in just between 2 samples. So what you see is this very interesting thing is I let this go forward and I keep taking more samples. I can actually see the relationship between these two. They're going at the same rate. My original one's going counterclockwise. It's taking samples around the unit circle. But the one that is the conjugate, or the n minus k, is actually going clockwise. And the reason it turns out to be the complex conjugate, where the cosine is the same but the sine is reversed, is because of that fact. So something that's going counterclockwise will be doing the opposite thing going up and down as the one that's going clockwise. But actually, if I look at what they're doing as the x changes, they're doing the same thing. Right now, they're both moving to the left in x. Eventually, they're going to reach the end. They're going to start moving back to the right in x. But you see, they're always the opposite of each other vertically. So that's why this is happening. All right, so that's interesting. And actually, this is the reason when you look at certain videos of like car wheels spinning, that they look like they're either stopped or going backwards. Because they're actually going so fast that you don't get enough samples to notice how fast they're going. And so I've linked a couple videos below that show this wagon wheel effect. That's what they call it. All right. So more generally, so I mean, this is the relationship between these pairs of conjugate frequencies in the complex DFT. But we can have this happen really for any frequency if we have a signal and we capture it with samples. So let me show you something. So here is a signal that has cosine of 10 hertz times 2, actually, plus cosine of 50 hertz times 2. Sorry, cosine of 50 hertz times 1, 50 cycles. What you see is, okay, let me start this over, actually. Okay, so this is 2 times cosine of frequency index 10 plus 1 times cosine of frequency index of 50. You know, the amplitudes get split between this and its conjugate, and that's fine. I'm using fewer and fewer samples here. Okay, and what you notice is as I use fewer and fewer samples, I mean, this retains its shape. You can see these bigger wiggles from the 50 cycle thing start to have fewer samples, so they start to look a little jagged, but I do still have the right number of wiggles. But eventually, if I run out of my sampling frequency here, suddenly I don't have enough wiggles anymore. This thing gets aliased. What it means is it's really a higher frequency, but I think it's a lower frequency. And then it gets really crazy at the end. Okay, so let's watch this one more time. Okay, yeah, I have different numbers of samples as I'm going through the whole thing. But it basically retains its shape. I mean, I might want more samples here. This looks a little jagged, but I can see it's got the right number of wiggles. But as soon as I get to 100 samples for a frequency of 50, I'm in trouble. I cannot represent frequencies that high. So it starts to look like actually even a lower frequency at one point than the other one. And then this really crazy stuff happens. Okay. So that's called aliasing. What does that sound like in audio? Well, let me do the following. So I created a square wave here. Let me just listen to the square wave by itself first. So I sampled a square wave at 44,100 hertz. I made it a square wave with a 440. So actually, you know what? I'll go even up an octave. I'll make it 880. So 1 octave above concert A. Let me also plot the Fourier transform here, and then we can listen to it. Okay, so let me just get the frequencies right here. Okay. And let me hone in on, let's see, I'll go from maybe, well, no, I'll look at the whole thing. That's fine. Okay, so here's my square wave. Actually, let me go down. We're getting some aliasing already. Let me go down to, oh, no, we're not, we're good. I meant to put this, okay. 880, okay. We are getting a little bit of aliasing, but it mostly sounds okay. And you notice this harmonic series, right? So here's my square wave. And I have this fall off in frequency and everything looks okay. I get the mirrors images on the other side, fine. Okay, but let me do the following. Let me actually make the sample rate go down by a factor of 6. And let me use a slice. So I'm going to take every 6th sample. So now let me take the Fourier transform of this, and I'll plot it, and we can listen to the result. All right, so let's see. First of all, I'm seeing something that is not looking too good here. This no longer looks like the square wave. I can see that some of the frequencies that should have been way over there. You know, it should be going down the sequence. They actually bounced. They got reflected back, right? So what does this sound like? Ooh, sounds pretty bad. Oh no, because I needed to. Okay, sorry, real quick. I need to also play it back slower. Okay, so that was the original. And in this one, we hear what's happened is some of the frequencies come in lower. We can actually hear them, some in the bass that are below the bass frequency here. We hear this kind of low buzzing. And we also hear like an inharmonicity, like some of the frequencies got reflected back, and they're no longer in integer ratios with the bass frequency, so it sounds really bad. Okay, I probably shouldn't keep playing that because it's horrible. All right, and so this is something to be aware of. I just want to show you also what this sounds like on real audio. So let me load in some real audio. So I'm going to load something that one of your classmates made, and we'll play it real quick. And I don't want to listen to what happens when I decimate it, when I just take one out of every so many samples. So one of your classmates made this.
May I have your attention, please? May I have your attention, please? Will the real Slim Shady please stand up? I repeat.
This FM synthesis.
Will the real DFT please stand up? Please stand up.
There we have it.
Please stand up. Please stand up.
So what happens when I take this and I decimate it in time? I say y is equal to x, and I'm only going to take every sixth sample. That's what I mean fact there. Okay, and let's listen to it.
May I have your attention, please? May I have your attention, please? Will the real Slim Shady...
Actually, that sounds okay. Let me load this in at a slightly lower sample rate to begin with. And let me do this again. There we go. So I can't even support the frequencies that are necessary to capture the voice there. So they come back and they sound really weird. They alias at lower frequencies. I mean, so the bass sounds just fine, right? That's not a frequency that we're worried about. But we're worried about the frequencies that are too high with regard to the sample rate. In particular, any frequency that is beyond half of the sample rate, which I think we can see by now, right? Any frequency that's beyond half the sample rate is going to alias if we don't properly filter it out before we sample. So that's the bottom line. You know, we can see that, right? This is the highest frequency here, which is the sample rate, pretty much sample rate minus 1. And so you can see, you know, half the sample rate, that's when I start to mirror back. And in the animation that I showed you a moment ago, that's when you see we run into trouble. When suddenly I only have, you know, the mirror image, which takes up half of this thing, starts to coincide with the first half. So yeah, we can start to get this really weird effect.
Will the real Slim Shady please stand up? I repeat.
Will the real DFT please stand up?
And actually,
Please stand up.
you can even hear it with some of the notes. They're not, the highest notes there aren't able to go high enough.
Stand up. Please stand up. Please stand up. Please stand up. Please stand up.
Let me see, and let's make it even more extreme. How about we take it down by another factor here? Yeah, we kind of really lost it up there. Because now we're down at, okay, so let's see. Yeah, we're down at 1837 in our sample rate, which means we're not going to be able to support frequencies that are more than about 900 hertz. So that's okay for all the bass, but it ruins kind of all the harmonics and everything else. I just really want to keep doing this because this is so cool. Let's try to drop it even more. So now we're down at 735 hertz. We probably won't even be able to make out the voice. Let's see. Yep. Because you know the bass frequency of the voice is beyond half of this. So anyway, that's aliasing for you. So, all right, I just want to, after this, I just want to point one more thing out about the short time Fourier transform, or about the complex DFT, and then we can talk more on Monday.